Well, good afternoon. Welcome to NASA headquarters. My name is Dwayne Brown with the Office of Communications. Today, you will hear the first of what will certainly be many more key science findings from NASA's Mars Atmosphere and Volatile Evolution Mission, or otherwise known as MAVEN. MAVEN and other Mars missions are helping pave the path towards NASA's journey to Mars, sending humans to the red planet in the 2030s. Ladies and gentlemen, MAVEN is helping answer a question that has been asked by scientists for decades. Where did the atmosphere and the water go? And could this same thing happen to Earth? We'll have brief presentations from our participants, and then we'll open up for questions starting here at NASA headquarters and go to our phone lines across the country and across from all the world. Social media is abuzz with Mars and the MAVEN mission. Twitter, Facebook, YouTube, follow the conversation. Send those questions in to hashtag AskNASA. We'll get to some of your questions on social media, and we're also, following this presentation, we'll have an hour-long session and perhaps longer to send in your questions and have some of the scientists answer your questions from all over the world. Hashtag AskNASA. And of course, you'll be able to follow all of this information and much, much more on the web at www.nasa.gov/MAVEN, and to Journey to Mars, www.nasa.gov/Journey to Mars. Before we get started, let me introduce you to our folks here and also joining us from Iowa and Colorado. First, Michael Meyer, lead scientist, Mars Exploration Program, NASA headquarters. Bruce Jakoski, MAVEN principal investigator at the Laboratory for Atmospheric and Space Physics, LASP, at the University of Colorado Boulder. And joining us from Iowa City, Jasper Helicus, the MAVEN Solar Wind Ion Analyzer Instrument Lead from the University of Iowa. And over at Colorado, Yasui Dong, MAVEN Science Team member at LASP, and Dave Brain, also at LASP, MAVEN co-investigator. So hold on to your hats and let's get started, and I'll toss it over to Michael.
Well, thanks, Dwayne. The NASA Mars Exploration Program has been focused on finding water. Water is the prime ingredient needed for life. It is a major factor in the climate and shaping geology, and is a critical resource for future human exploration. We have visual and mineral evidence of water on Mars from orbit. We have rovers that have found rocks that formed in aqueous environments, and we've even found evidence that ancient Mars had enough water to support microbial life. So we've looked for water and we found it. But if you look at Mars today, it's a cold, dry, desert planet. What happened? Mars lost its atmosphere. Well, how did that happen? The atmosphere of Mars could have frozen out. It could have been turned into rocks. It could have been knocked off by asteroids or comets, or it could have been stripped from the planet by the solar wind. To answer this question, NASA has sent the MAVEN mission to Mars. That mission was designed to look at the upper atmospheric processes, see the interaction with the solar wind, and basically get a better handle on atmospheric loss. So what happened? So we are looking at a mission that is completing its prime. It has been under budget, it's been on time, and it's behaving beautifully. So to answer the question, what happened to the Mars atmosphere, I'll quote Bob Dylan. The answer, my friend, is blowing in the wind. So, and to give us some more detail, I'll turn the mic over to the principal investigator of the MAVEN mission, Bruce Jakoski.
Thank you, Michael. The MAVEN spacecraft has been orbiting Mars since September of 2014. We're coming up on the end of the one-year primary mission. The mission lasts for another 10 days, actually, and we'll be beginning an extended mission after that. The spacecraft and all of the science instruments are working well, and we're here to tell you today about some of the results that have come out from the first 6 months or so of data analysis. It's taken a long time to get to this stage because the type of instruments we have on MAVEN are not instruments that can instantly be interpreted. They require analysis and calibration in order to be sure that we understand what's coming out of that. So it's taken a while to get here, but we have results that we think are exciting. We're going to talk about the history of climate on Mars. MAVEN was designed to understand the changes in climate. If we can roll the first video, please. Today's planet is a cold, dry, desert-like environment. The atmosphere is thin. It's not capable of sustaining liquid water at the surface today. It would either freeze or evaporate very quickly. However, when we look at ancient Mars, we see a different type of surface, one that had valleys that looked like they were carved by water, lakes that were standing for long periods of time. We see an environment that was much more able to support liquid water. The climate must have been very different, warmer and wetter, and the atmosphere must have been thicker at that time in order to sustain a warmer climate. So what happened to the carbon dioxide from that early atmosphere? What happened to the water from early Mars? MAVEN is exploring the ability of the atmospheric gases to go to the top of the atmosphere where they can be stripped away by the solar wind and by the sun to space. We're studying the top of the atmosphere because that's the conduit, if you will, through which the gas has to travel to go from the main part of the atmosphere to where it can get removed to space. We're going to look at a lot of different processes that can take place in removing the atmosphere, but we're going to focus largely today on the ability of the solar wind to strip the gas away. If we can roll the second video, please. We're looking at the solar wind as it impinges on the planet. The solar wind is streaming out from the sun at about 1 million miles an hour and is able to grab ions from the planet and strip them away from the planet or knock them into the planet at very high speed and knock other stuff off. We're going to be talking today about the role of the solar wind in stripping the atmosphere, and we'll be hearing about the behavior of the solar wind and the consequences of loss to space. Dwayne?
Thank you, Bruce. And let's get into more of those details. Let's go to the University of Iowa in Iowa City and Jasper Halikas. Jasper?
Thank you, Dwayne. So I'd like to first set the stage by describing a little bit about how Mars interacts with its environment. If I could have my first graphic, please. Mars has something in common with the Earth and the other planets, and that, of course, is the influence of the sun. As you see in both of these graphics, all of the planets, Mars and Earth and the others included, are impinged upon by this flow of charged particles from the sun that we call the solar wind. These charged particles stream out from the sun at about 1 million miles an hour, and they impact all of the planets in our solar system. Now, the Earth and Mars have something that is very different, however. As you see on the right panel of this graphic, the Earth has a strong global magnetic field, and that magnetic field largely shields its atmosphere from the direct impact of the solar wind. On the left, on the other hand, Mars has no such global magnetic field, and its upper atmosphere lies completely exposed to the solar wind. As a result, the solar wind can interact with that upper atmosphere and strip portions of it away into space. Now, Mars has only a thin atmosphere today, and compared to the Earth, say, or Venus, but it's still thick enough to stop the solar wind from hitting the surface of Mars. Instead, the solar wind is deflected around the planet. And I'm about to show you a movie which shows this. If I could have my second graphic, please. The movie that you're about to see shows the trajectories of the solar wind as they pass by Mars. The solar wind will be coming in from right to left, and you see that it's deflected around Mars in a conical shape. Now, you might notice that that shape is very reminiscent of the shock wave in front of a supersonic jet plane, and that is no accident at all. It's exactly the same kind of a shock wave that's formed. Now, behind the simulated solar wind trajectories here, you're seeing actual MAVEN data taken from the first year of our mission at Mars. The colors there are showing the density of the solar wind plasma, the number of charged particles from the solar wind, and the little vectors show the direction that that solar wind is flowing. This data shows exactly what you just saw in the simulated solar wind, which is that the solar wind comes in, it is shocked, you see the density jump up from blue to red there, and it is deflected around Mars. But that solar wind flow continues in past that outer boundary and continues into the inner edge of that red region that you just saw on the graphic. And it's at that point where the rubber hits the road. There's a second boundary there where the solar wind interacts directly with the upper atmosphere. This is unlike anything that we have at Earth. Now, as a result of the magnetic and electric fields that are carried with that solar wind flow, ions which are born in the atmosphere of Mars can be accelerated up to escape velocity and beyond, and we believe this is an important process by which the Mars atmosphere is lost today. Now, this whole interaction picture changes as a function of how hard the solar wind is blowing. If the solar wind is just a gentle breeze, then this interaction picture expands, puffs outward. If the solar wind is a strong gale force wind, then this whole picture is compressed downward towards the surface. A natural question you might ask is, well, what does that do to the loss rate of atmosphere from Mars? Well, we've conducted an experiment to try and answer that, or rather nature has conducted a wonderful experiment for us. If I could have my third graphic, what the sun has done for us is launched a dense bubble of extremely energetic charged particles outwards. In this third graphic, which you'll see in a second, the charged particles from the sun stream outward at double their normal velocity. Instead of the normal 1 million miles an hour, this bubble jets out from the sun at 2 million miles an hour, carrying a tremendous amount of energy. As it plows through the matter in front of it, it develops its own shock wave. So what you might imagine now is that you have two jet planes, each with their own supersonic shock wave approaching each other, but one of them is thousands, tens of thousands bigger than the other one. If you actually did this, things wouldn't go well for the small plane. Mars, which is the small plane in this analogy, is a little bit more robust, but it's very strongly impacted by the energy that's delivered by this event. It compresses the magnetosphere of Mars, the protected region around the planet, down to about 2/3 of its normal size. And as a result, more of the atmosphere is exposed to these fields that strip away particles from the atmosphere of Mars. In fact, we see that the atmospheric loss rate during this event goes up by a factor of between 10 and 20. So it has an enormous impact on the upper atmosphere of Mars. Now I'm going to throw it over to Yashui Dong at the University of Colorado, and she's going to tell you about some of the processes and the channels by which these charged particles are actually lost to space.
Thank you, Jasper. So Jasper has talked about the solar wind interaction with the Martian atmosphere. Next, we are going to talk about the consequence of this interaction, the ion escape from Mars. And can I have the video, please? So first, we will show a simulation video. We are looking at the solar wind hits the Martian atmosphere, and it also carries a magnetic field with it. The moving magnetic field will generate an electric field in the upward direction in this video, and this will cause the planetary ions to move and escape from Mars. Some ions are accelerated by this electric field very quickly. As you can see that they form this upward plume from the day side of Mars, which looks like a fountain from the top of the Mars. Meanwhile, some other ions will drift around Mars and eventually escape in the solar wind direction, and they will form this tail behind Mars in the night side. And the MAVEN spacecraft is able to measure the ion compositions and the velocities. And here shows the MAVEN measurements of the escaping oxygen ions from Mars. These arrows represent the measured ion moving directions. As you can see that the data we have here matches the simulation results very well. And can I have the next graphic, please? So next, we are going to take a closer look at the MAVEN data. So from the data, we can clearly identify 3 ion populations by their different regions and moving directions. First, in the upper hemisphere in this figure are the plume ions moving in the electric field direction. And the red and yellow colors in this region mean that there are many ions escaping through the plume. And such a substantial plume of escaping ions from Mars has never been conclusively identified from previous observations. So MAVEN actually provided the first observational support for the plume as a major feature of the Martian atmosphere. And second, if you look at the night side of Mars in this figure, there are also many ions escaping in the tailward, which is also the solar wind direction. And the other thing you can tell is that the plume ion velocities are significantly higher than the tailward escaping ion velocities, as shown by these longer arrows in the plume region. Third, in the lower hemisphere of this figure, there are ions coming toward Mars. These ions are generated from the very tenuous neutral corona. The neutral corona is the extended part of the Martian atmosphere, and these ions are moving toward Mars as carried by the upstream solar wind. And from the different colors in this map, we can tell that most of the ions are escaping through the plume and the tail. So the plume and the tail are the two major escaping channels for planetary ions at Mars. And can I have the next graphic, please? So based on all these observations, we can estimate the plume to contribute about 25% to the total ion escape, and the tail to contribute about 75%. And this is the first time that we can confirm from observations that the plume is an important planetary ion escape channel from Mars. And also the first time we can quantitatively estimate the contribution from the plume to the total ion escape. So next we will have Dave to talk about the total ion escape rate at Mars. Thank you.
Okay, thank you, Yashwei. And Yashwei showed the different paths that ions or charged particles from the Martian atmosphere can take as they're leaving the planet. And the next step is to be able to add all of them up to figure out how many are leaving at once. So if I can have the first image, please. One way of getting an answer to this question of how many particles are leaving is to imagine a sphere around Mars, an imaginary sphere around Mars at high altitude above the surface. And every time the MAVEN spacecraft passes through this sphere, we can look to our observations and ask whether there are a lot of particles leaving the planet or not very many at all. A lot of particles are indicated in these figures by dark blue colors, and not very many are the lightish blue or whitish colors. And so over time, over many orbits and many months, we can paint a picture on this sphere of where ions are leaving in abundance and not so much. And the figure suggests two things to me. There are two things that come to my attention. Number one, the colors are not evenly distributed around this sphere. On the night side of the planet, you saw a lot of dark blues, and also at the top and the bottom of the planet as well. This is consistent with what Yashwei just showed, where there are many charged particles leaving on the night side and from the top of the planet. By contrast, at the center of the day side, you see lots of white and lighter colors. There are not very many charged particles leaving from that location. This is also consistent with the observations and the simulations that Yashwei just showed. So these maps provide a statistical picture of where ions are escaping in abundance from different regions, but to get a global escape rate, how much is escaping from the entire planet at once, we simply have to add up the data that are represented on those maps. When we do that, we get a number. We get a few or several times 10 to the 24 atmospheric particles leaving the planet every second. And that's a really big number, and I personally have a hard time having any intuition for a number that has an exponent of 24 in it. So it's much more convenient for me to think of it in terms of mass. How much atmosphere, what's the mass of atmosphere escaping every second? And when we do that, we find that there are roughly 100 grams of atmosphere escaping every second, or about a quarter pound of atmosphere escaping every second. And I can't help but imagine hamburgers flying out of the Martian atmosphere, 1 per second. But fortunately, it's instead oxygen and carbon dioxide that are leaving the planet, which are important both for water and for the climate of the planet overall. So this escape rate that I just gave you is a lower limit for a couple of reasons. First of all, we've emitted low energy charged particles from the maps to this point, and also neutral particles, atmospheric particles that lack any electric charge. When both of those things are ultimately included, the escape rates that we report will only go up. So this was an average escape rate for today's conditions, but there's no expectation that that escape rate has been constant over the history of the planet, as Jasper mentioned. So if I can have the next graphic, please. In the left panel of the graphic, you see Mars under normal conditions today, where the solar wind is flowing towards Mars and interacting with the atmosphere, and the rainbow-colored atmospheric particles are escaping the planet in many different ways along many different paths. In the right panel of the figure, you see Mars under very different conditions when one of these solar storms passes by and engulfs the planet. When that happens, as we've observed with MAVEN, the escape rates go up, and they go up by a factor of 10 to 20 at least during one of these solar storms that MAVEN observed, and it's by no stretch the largest solar storm that Mars has ever seen. This is exciting to me, to think that events like this increase escape because solar storms were more common and more intense earlier in solar system history. So long ago, we expect escape, like is shown in the right-hand panel, to have been happening all the time and stripping away lots of atmosphere from the planet. This implies that not only is the Mars atmosphere escaping today and has been escaping over time, but much of that atmosphere may have been lost early on. So the MAVEN observations are teaching us how the atmosphere of Mars has evolved, and understanding those effects will not only help us to understand the Mars atmosphere, but I'm hopeful that they'll help us to understand how atmospheres everywhere interact with their star and their space environment, including planets orbiting other stars. So with that, I'll pass it back to you, Dwayne.
Thanks, Dave. And for some reason, I have a craving for a hamburger, so I don't. Thank you, University of Colorado and University of Iowa. Before we open it up for questions, starting here and across the country, give the principal investigator an opportunity to summarize why these findings are so significant. Bruce?
Thank you. What we've seen is that for the first time, we have measurements that tell us not only the escape rate of gas out the top of the atmosphere and lost to space, but the processes that control it. And this is important because if we want to look backward in time, we can't just extrapolate the process, the escape rate without understanding how escape is occurring. When we look at the processes, we see that many of them would have been greater in the past. The escape rate today, 100 grams per second, is not a very large number. It's enough to remove the entire atmosphere in a couple of billion years, but not enough to account for the thick early atmosphere. However, when we account for the greater loss rates early in history, we think that loss to space, that stripping by the solar wind, was an important process in the changing climate of Mars. And that's what we're really trying to aim at. We're continuing the observations. We have an extended mission. We'll be looking at the second half of the first Mars year that we've been there, and we'll be looking at the changing conditions through the solar cycle. So I'm looking forward to a much improved understanding as we get into this. Dwayne?
Thank you. Okay, so before I ask the media in the room to raise their hand and wait for the mic, I want to recognize another member of the incredible MAVEN team, the program scientist, El-Sayed Talat, and he may chime in on some of the questions we have. We have a number of media on the phone, and of course, social media is abuzz with questions. So are there any media here in Washington? Okay, let's see if we can, let's go ahead and go to social media. And Emily, what's the buzz out there in the social media world?
Yeah, there's a lot of questions. So this question was asked by a lot of our followers. Is this same effect occurring to the Earth now, or could it happen in the future?
Let me turn to Dave Brain to answer that one.
Dave, did you copy that question?
I did. So the question was, can the same kinds of things happen to Earth now or in the future? And the answer is mostly yes. Earth is losing atmospheric particles. But as Jasper said, Earth has a big global magnetic field that shields the atmosphere from the solar wind. So some methods, some pathways that particles can take to escape the atmosphere of Earth are basically choked off compared to Mars. Other processes that we observe at Mars and are observing with MAVEN do occur at Earth. For example, the loss of particles that lack any electric charge and escape out of the polar regions of Earth's magnetic field. And so there are things that we can compare between what we're observing with MAVEN and what's going on at Earth even today. And then the second part of that question is Earth in the future. And it may be that someday, a long time from now, Earth's magnetic field shuts off because of a lack of interior heat in the planet. When that happens, Earth becomes like a large version of Mars with all of the same escape processes occurring. Between now and then, there are time periods when the Earth's magnetic field reverses, and those reversals can take a couple of hundred years at a time. During those time periods, Earth's atmosphere is left largely exposed to the solar wind. However, 100 or 200 years is a relatively short time in the grand scheme of things, and so the atmospheric escape during those time periods should not be significant enough to really damage or impair the climate of Earth in a very large way.
Let me also add that most of the stripping by the solar wind at Mars was thought to have taken place very early in the history of the solar system, when the sun was much more active, when the solar wind was more intense. So today the rate of loss at Mars is low. During those times when the Earth might be losing atmosphere, the rate of loss would be low. So we don't have anything to worry about in terms of the Earth's atmosphere disappearing on us.
Emily, 2 more questions, and then we'll go to the phone lines.
Great. This one's from Trey on Twitter, and he asks, can you simplify what happened to the atmosphere and water on Mars? Is there an easy to understand analogy?
The solar wind stripped it away. The analogy that I use is when I step out of the shower into the breeze, the water in my hair is just whisked away by the wind. Mind you, this is an increasingly theoretical construct.
Hey, one more?
Great. This one is from Dustin on Twitter, and he said, is it possible to reverse the effect of Mars losing its atmosphere?
People talk about terraforming Mars, taking the CO2 that might be locked up in the crust and putting it back in the atmosphere. If that's where all the CO2 had gone from an early thick atmosphere, that might be possible. But with it having been stripped away to space, it's not there. It's been removed from the solar system entirely, so it's not possible to bring it back.
Okay, we'll come back to social media and send those questions in again at #AskNASA. And again, a reminder that following this, we will have some of the scientists get together and answer all of the questions if we don't get them answered here today. But let's go to the phone lines. And first up, we have the Houston Chronicle, Mike Tolson. Mike?
Yes, this is for Bruce. My question is whether any other element, any other factor could have also contributed. Of course, in popular fiction, we've seen the speculation of an asteroid impact having decimated some of the atmosphere. Is there any other factor that you have been able to discern or even speculate about which also would have contributed to atmospheric loss besides the solar wind?
There are a lot of processes that have the ability to remove gas from the atmosphere. Michael mentioned some of them at the very beginning. It can go down and form carbon-bearing minerals or water-bearing minerals in the crust. You mentioned the ability of an asteroid impact to knock gas off. We've been focused on understanding the processes involving the sun as an energy driver at the top of the atmosphere. So we see evidence for stripping by the solar wind, for a process called sputtering, in which these accelerated ions can hit the atmosphere at high speed and eject other stuff off to space. Thermal escape, in which the fastest hydrogen atoms that come from water can just be fast enough to escape the planet directly. Photochemical processes. We're trying to piece together an overall picture of what happened to the water. And we need to look at Mars as an integrated system with a lot of different processes taking place. So we're putting together this piece of the puzzle. You can do theoretical models that look at the role of asteroid impact. Certainly early in the history of the solar system, that was an important process, but it's probably not much of an ongoing process today. So it's very hard to study empirically.
Next call is from Alan Boyle. Alan?
Thank you. On this issue of how quickly the planet may have lost its atmosphere due to solar storms versus the typical solar activity, is there a way to tease out that question? Are those solar storms from the primordial days of the solar system really the culprit here, or how much of a factor might you be able to find out that happened to be? Thank you.
That's a really good question, and I don't have a really good answer yet. What we know is that the rate of removal of gas during a solar storm goes up by a factor of 10 or 20 in the one event we've examined in detail, and that solar storms would have been more abundant early in history. We also know that the solar wind, as a steady ongoing process, can remove gas, and that rate would have been greater early in history. Together, we think that these would have been very important processes, but we haven't done that extrapolation backward in time yet, so it's very hard to give a quantitative estimate today of which was the most important process.
And also, Bruce, just to remind everybody, early on in Mars history, Mars actually did have a global magnetic field, so it had protection for a while until it cooled off enough that its dynamo stopped. So that period of time is, under debate about when exactly it lost its magnetic field and then experienced much more significant atmospheric loss.
Next up is Camille Carlisle. Camille, Sky and Telescope Magazine. Camille?
Hi. Two questions. One, a smaller one. Which flare CME event was it that you saw the spike in? Was it the one from last year where there were aurora, or was the one from this past March? And then I have a second question.
We were looking at the event in March of this year. It was actually 3 events, one right after another. Mars is never easy. You can't examine a single event in isolation. The sun had to throw several events at us, so we have to separate out the different effects. We did see aurora as a result of this event, though. The energetic particles did trigger aurora with that event as well as the earlier one.
Okay.
Next up is Eric Berger. And Eric, if you can give your affiliation before you ask your question. Thank you, sir.
Yeah, thank you for doing this. This is Eric Berger with Ars Technica. I was wondering if this information from the atmospheric loss to the solar system has given you any better estimate of when Mars would have been conducive for surface water, lakes, rivers, things like that kind of carved its features, millions or billions of years ago.
From the geology, we get a good estimate of the timing of when Mars had water. Up until about 3.7 billion years ago, water seemed to be very abundant and active. So the stripping of the solar wind, the stripping by the solar wind of the atmosphere would have occurred in that same time frame. That's when the extreme ultraviolet photons from the sun, when the solar wind were most intense. So we think that the loss of the atmosphere occurred over a few 100 million years, from about 4.2 to maybe 3.7 billion years ago.
Next up is the Ken Kramer. Ken?
Doing this, and congratulations on the results. Yeah, I was interested actually in your updated thinking, which you kind of just answered about when the water was lost. Maybe you can review that a little bit more. How long do you think how long did it take to lose the magnetic field, and how long did the water last and in liquid form on the surface, and how long what was the loss required to have a tremendous loss of water? How much more did it have to be? If it's only 100 grams a second per day, can you give us an estimate of what it would have to be to cause a tremendous loss in the past? Thank you.
What we think, as Michael said, what we think is that the early magnetic field that Mars had would have protected the planet from direct impact by the solar wind and would have kept it from stripping gas off. So it would have been the turn off of the magnetic field that would have allowed the turn on of stripping of the atmosphere by the solar wind. The evidence suggests that the magnetic field disappeared about 4.2 billion years ago. The amount of gas that we think would have to have been removed, let me start back with the current Mars atmosphere, which has a thickness of 6 millibars. That's just under 1% as thick as the Earth's atmosphere. we think that you would have to remove an amount of gas about equivalent to what's in the Earth's atmosphere. So the rate would have been would have to have been a factor of maybe 100 higher in order to be able to remove the gas early in that time period, 100 to 1,000 times higher. And that's consistent with what some of the models have predicted the loss rate back in early history would have been.
Okay, we're going to go back to social media. And Emily, back to you. We'll take 3 more questions, and then we'll go to our phone lines, and then we'll wrap up. Emily?
Cool, thank you. This question's from Wes, and he asks, how does the new information like today's announcement shape future research on Mars? What should we look at next?
Let me give a try at that one. That's an important question, because one of the things that we've learned, not just from MAVEN, but from the whole suite of missions that we've sent, Curiosity and Opportunity, Mars Reconnaissance Orbiter, Mars Odyssey most recently, is that Mars is a very complex system. You can't study the geology in isolation from everything else, or the atmosphere in isolation from everything else. It's a very complex, coupled system. So when we want to learn, for example, about life, the potential for life, we have to study the atmosphere, the geology, and now we have to study the upper atmosphere to learn about the history of the climate. All of these play a role because the gases can exchange between all of these places. All of them represent important processes. So MAVEN is filling a gap in our understanding where we had really very little idea of how the upper atmosphere operated and of what processes played a role there. This feeds back into our understanding of the behavior of the climate as a whole and what drove climate change on Mars, and that feeds back into issues related to the potential for life. And I brought it back to the life question because that's really at the center of a lot of scientific exploration of Mars. Mars appears to meet all of the conditions required for life, or to have met them at the surface in the past. And that begs the question of whether there was ever any life there, and then if there was, whether it's genetically related to terrestrial life or would represent an independent origin. So as we go into the future, I think these questions about life and climate and the history of the planet as a whole really are at the center of the exploration.
Emily, 2 more?
Yeah, sure. This one's from Dakota, and he asks, if this atmosphere, I think you sort of touched on this as well, but if this atmospheric erosion from the solar wind is still happening, will Mars eventually have no atmosphere at all?
At the current rate of escape, it would lose its entire atmosphere in another couple of billion years. But we think that the gas in the atmosphere isn't all that's there. There's gas locked up in the polar caps. The atmosphere exchanges with gas in the top meter of the subsurface and deeper to the top tens of meters. So one of the questions about Mars is, what's the total volatile inventory? How much gas is there anywhere on the planet? As we remove gas to space, we think that it is probably being replenished from these non-atmospheric reservoirs. So I think the atmosphere is not going to disappear in the next couple of billion years, but I can't tell you exactly what it's going to be like either.
1 more, and then we'll go back to the phones.
Sure. This one's from William, and sort of branching off of that, if there was liquid water found on Mars, wouldn't that prove that there's still atmosphere that's sustainable to some type of life?
The question of liquid water is at the heart of this, and the reason we flew the MAVEN mission is to understand the history of liquid water by looking at the climate. Water could have existed at the surface early in history, and it was stable. But water can exist at the surface today, but as a transient. And some of the recent measurements from the Mars Reconnaissance Orbiter suggest there might even be trace amounts of liquid water occurring intermittently, even at the present epoch. So we have this contrast of global scale liquid water that has evolved along with the climate over 4 billion years and is being explored by MAVEN, and tiny amounts of transient liquid water that might be present today. It's all part of this picture of understanding the behavior and history of liquid water.
And to add to that, Bruce, a little bit is the suspicion that there's still water on Mars. We certainly have measurements of ice showing that it's at the poles and in the mid-latitudes, but also the suspicion that maybe there can be aquifers on Mars. So if life ever did get started, perhaps the habitable place on Mars today would be in the subsurface, where liquid water is still a reasonable presumption.
Okay, ladies and gentlemen, we're coming up about 15 minutes or 20 minutes. What we're going to do here is we're going to go to the phone lines. We're going to take 3 more calls, and then we have a question here at headquarters, and we're going to end the briefing. For social media, keep those questions coming in at #AskNASA. Again, we will have a team of scientists answering your questions later today. And for the media that we don't get to on the phone, we will make sure that scientists are available to do any one-on-one interviews following the press conference. So let's start with Adrienne Lefranc. Hope I got that name right, Adrienne, from The Atlantic. Adrienne?
Thanks for taking my question. I understand that the unusual auroras on Mars also inform your understanding of atmospheric loss, and I'm hoping you can describe just sort of in vivid detail what an aurora on Mars looks like, how it's different from the appearance of northern lights on Earth.
And let me ask Dave Brain if he can take that one as well.
Sure, thanks. That's a great question, and aurora on Mars are really exciting and really interesting. And there are essentially 2 kinds of aurora on Mars that have been observed. One that we knew about even before MAVEN arrived, and these are aurora fairly similar to Earth's aurora at the North Pole and the South Pole that take place in really small-scale magnetic fields that are associated with specific regions of the Mars crust. And the big difference there is that the Mars aurora in the small magnetic fields are weaker than those observed at Earth. But the excitement for MAVEN is that a new kind of aurora was observed at Mars that frankly surprised us. And this was aurora in a part of the atmosphere that is above regions that don't have any magnetic field at all. And it's strange to think about, based on our personal experience, aurora that don't take place in magnetic fields. And not only did we see aurora on Mars in the form of ultraviolet light detected by MAVEN's instruments, but we also saw the particles that went crashing into the atmosphere to create them. And these are very energetic electrons that come from the sun. And those intense electron events are at least rare in MAVEN's experience. They've only happened 2 or 3 times since we've been there, including around Christmas 2014. So among the team, we're calling those the Christmas lights. But they also happened during the solar storm that Jasper talked about in his comments as well. So we've seen these aurora in ultraviolet, and it's possible that the new kind of aurora lights up the entire night sky over much of the planet. And you can do model calculations of whether those aurora would be visible to the naked eye. And those model calculations are still premature, but a good guess is that they may be visible to the naked eye, so that if you're standing on the night side of Mars in a place where there's no light pollution and you're looking up at the sky, you could see the whole sky light up during one of these events. It would be magnificent.
Thank you, Dave. Next up is Frank Mooring from Aviation Week. Frank?
Thank you. Dr. Jacotsky, you mentioned earlier that comet impacts might have had a role in the loss of Mars's atmosphere. I wonder if you can say yet whether the passage of the comet sighting spring close to Mars last fall might have had the same kind of effect.
We did have the opportunity to observe one comet pass by, as you mentioned, comet sighting spring. It passed by only 140,000 kilometers away from Mars, and we were able to make some observations of the effects that it had on the upper atmosphere of the planet at the time. We saw the dust that was deposited from the comet into the atmosphere, and perhaps hints of some other things. The dust coming in has the ability to change the composition and to drive chemical processes in the upper atmosphere, but comets are relatively rare. Perhaps more significant is the regular interplanetary dust that's coming in all the time. This has its origin with comets, but it's not associated with a specific comet passing by. It's just always there, always coming in. MAVEN, in fact, has for the first time detected what we think is this dust coming in from interplanetary space, and it would have the effect of producing a long-lived, long-standing layer of metal ions in the upper atmosphere and creating a layer in the ionosphere. And the energetics of that, the chemical processes driven by that, may be affecting the atmosphere as a whole. So we see this dust, whether it's from comets or interplanetary dust, as a possible driver of energetic processes in the upper atmosphere that can lead to escape or can contribute to escape, but it's not a direct connection. And I couldn't tell you today how much escape it's driving.
Next up, we have Tracy Watson from USA Today. Tracy?
Yeah, hi. Thanks for taking my question. So I understand that you've kind of quantified the amount of atmospheric loss that can occur during a big solar storm, but can you help me out to understand how this gets you closer to understanding what happened eons ago? Because from what I heard today, you haven't quantified whether the storms were enough to strip away a large part of the atmosphere. Thanks.
The ideal situation would have been to observe the solar wind early in Mars history as it was stripping away gas from the atmosphere, but NASA tends not to fund 4 billion year-long missions, so we settle for looking at the atmosphere today, understanding the processes and trying to extrapolate backwards in time. Today, the main result that we're talking about is a much better understanding of the loss out the atmosphere today and of the processes driving it. I'm only waving my arms a little bit on what this did over time because the team has been so focused on what's going on today that we haven't had the chance to do that extrapolation backward in time. But all the indications are that the loss rate at the greater rate appropriate for early in history would have been adequate to remove a very large atmosphere and take us from a warm, wet planet early in history to the cold, dry planet today. So I'm going to have to ask you to hang on until we can do that analysis, and then we'll give you a much more quantitative estimate.
Okay, one last question from the phone, and then we'll come here in Washington. Tom Ricin from US News. Tom?
Yes, thank you. Congratulations to the MAVEN team. I'm curious, after doing all this in-depth study of climate change that happened to Mars, what kind of lessons do you think it could have for people who are studying how Earth's climate is evolving or could change rapidly?
The processes that we're looking at for driving Mars climate change are thought to be very different from the processes that drive Earth climate change, especially when the climate change, when you use those words here for the Earth, most people think that applies to the potential for human-induced climate change. So it's really comparing apples and oranges. There's not a direct comparison that I want to make, but we do get a better understanding of atmospheric processes in general. Michael, do you want to add anything to that?
No, I think that's about right. I mean, certainly Mars, all the climate change that we've seen has been induced by the failure of the global magnetic field on Mars, and then the consequences of interacting mostly with the solar wind. On Earth, it's an entirely different story in which we are seeing human-generated heating of the atmosphere.
Okay, if you can give your name and affiliation and your question, please.
Thank you. Marcia Freeman with the Executive Intelligence Review. We've had little atmospheric stations on the surface of Mars on a number of landers for a number of years. And you mentioned that some of the solar wind processes could be accelerating ions, not just to escape, but various other, down rather than up. Is any of the data from any of the surface instruments useful for the study that you're doing? And sort of contingent to that, would it be helpful for you to have balloons, right? And something in between the surface and an orbiter?
There is an experiment on the Curiosity rover that's very relevant to what MAVEN is measuring. It measures the radiation environment at the surface. And the particles that make it to the surface are the same particles that hit the top of the atmosphere. So one of the things we're hoping to do is to couple those measurements together and with measurements at the top and at the bottom of the atmosphere, really understand what the radiation environment is and what drives it. In terms of climate, we've had multiple stations at the surface. We also have climate-related measurements being made from orbiting spacecraft. For example, the Mars Climate Sounder on the reconnaissance orbiter, which is measuring the properties of the main part of the atmosphere. All of this couples together, and by measuring the different pieces of the atmosphere at the same time or even at different times, we can understand the coupling between them. To give you one example, by understanding the lower atmosphere, we understand the ways in which atmospheric waves generated in the bottom part of the atmosphere can work their way up into the top of the atmosphere and deposit energy and mix things up. And that's an important component of understanding the behavior of the upper atmosphere. So again, I want to come back to this theme of Mars as a very complex system in which all the pieces are coupled together. And we need to understand each one separately, but also how they couple together.
Okay. Well, we're going to wrap up here. Let me first thank our folks that have joined us from our universities. First, Jasper Helicus from the University of Iowa in Iowa City. Thank you again, Jasper. And of course, our folks at the University of Colorado, Yashui Dong and Dave Brain. Again, keep those questions coming in on social media at #AskNASA. Team of scientists will be answering your questions as quickly as possible. For media, we will be taking your calls and requests and set up team members to answer your questions. And of course, all of this information and more is online at www.nasa.gov/MAVEN. Thanks for joining us. The journey to Mars continues.
Thank you. Yeah, thank you guys.